Manufacturer produces a storage tank. The tank's modelled in the shape of a hollow circular cylinder, closed at one end, with a hemispherical shell at the other end, as shown on the right. The walls of the tank are assumed to have negligible thickness. The cylinder has radius r, height h, and the hemisphere has radius r, all of this shown, and the volume of the tank is 6. Show that according to the model, the surface area of the tank in meters squared is given by this formula here. Right, where to start? Do we start by working out the volume or do we start by going straight into the surface area? I decided to go for the volume because that's an equation I can write down that relates h and r together. Definitely going to need that. So V will be the volume of the hemisphere, that's half a sphere, so 2/3 pi r cubed, plus the volume of the cylinder, that's going to be pi r squared h. It's the area of my cross section multiplied by the length of the prism, the cylinder. And that, remember, is equal to 6. Okay, I'm now going to write down the surface area. In fact, I'm going to do it in a different color. So that will be the surface area of the hemisphere. So again, half of the sphere will be 2 pi r squared. Plus, I'm going to deal with the bottom next, pi r squared as well. And then it's the curved part. So you've got to remember that when you take the cylinder, imagine you were to unravel it, you would actually get a rectangle, and it would have height h, and this length would in fact be the circumference of this circle, so 2 pi r. So I'm adding, actually in fact I can include it here, 2 pi r h. Now you see in the final answer, s is just in terms of r, so we need to replace that h by an expression in terms of r. And that's where this first part comes in. We can make h the subject. So pi r squared h is actually going to equal 6 minus 2/3 pi r cubed. Therefore, h is going to be 6 over pi r squared minus 2/3 pi r cubed over pi r squared. That's actually going to cancel down to 2/3 r. And I can now substitute that in. So s is going to be 3 pi r squared plus 2 pi r multiplied by 6 over pi r squared minus 2/3 r. And I can expand this bracket. So I'm going to get 12 pi r over pi r squared minus 2 times 2/3 is 4/3. And then pi r times r is pi r squared. These pi's cancel. This r cancels with that one. And then 3 is actually 9 over 3. Okay, I put it over a common denominator. So I've got 12 over r. Then 9 over 3 pi r squared minus 4 over 3 pi r squared gives me 5 over 3 pi r squared. And that was what we're asked to find. And so to summarize, I wrote down the volume, equaled it to 6, left that for the time being. Wrote down the surface area in terms of r and h, simplified it slightly, then actually made h the subject on the left because we had an equation, it was equal to 6, substituted that in, it gave us a definite relationship between h and r, rearranged it, well, like, simplified it, giving us a surface area that's just dependent on r because h is dependent on r as well. So now we're being asked to minimize the surface area. Okay, find the radius when the surface area is a minimum. And for this, we can use differentiation. This is what it's all about. We can optimize because s is a function of r. There's going to be a peak somewhere and a minimum somewhere. We're interested in the minimum. So we're going to find ds by dr and then set it equal to 0. Now 12 over r is actually 12r to the minus 1. I'll just write that for a second. So when I differentiate it, I will get minus 12r to the minus 2, which I can then write as 12 over r squared. And then I'll differentiate the r squared to make it 2r, so I'll get 10 over 3 pi r. That's equal to 0 for the stationary points. I'm going to multiply through, actually, I'm going to first of all write 10 over 3 pi r is equal to 12 over r squared. Then I'm going to multiply through by r squared. Now I'll times by 3, divide by 10, and divide by pi. So r cubed will be 36 over 10 pi, which actually simplifies to 18 over 5 pi. Not that that really matters. And therefore r is going to be the cube root of all of that. Cube root button here. Just realized I'm not using the right calculator here, and not the official A-level one, but it's okay. Don't need it. Which gives us 1.04644. And I'll just round it to 3 significant figures. Gives me 1.05 and then meters. Good, so that's how we can find the radius for when it's a minimum by setting the derivative equal to 0, or calculating the derivative and then setting equal to 0. And finally, we're just asked to calculate, we're not asked to show that it's a minimum, by the way. I'm always a little bit unsure in these questions whether it wants us to do that. I did check the marks given it doesn't, but we haven't technically shown that the radius leads to a minimum. That's all I'd say. But we've had to do quite a lot of work. I think if I was in the exam and I had a bit of time, I might just go back and do it again, find the second derivative and show that it's going to be positive. That would show it's a minimum, but it is okay in this case just to get the 1.05. In part C, we're asked to then calculate the minimum surface area of the tank. So we just need to sub it back in to that into the formula that we found before, this one here, in fact. So S min is going to be 12 over. Now, I would advise that you use the non-rounded answer here, because otherwise we're introducing rounding errors, and we're squaring this number and everything. It could make a bit of a difference, especially to 3 significant figures. So we can put this into our calculator, although you can just use the answer button to be fair. So 12 over answer plus 5 over 3 pi times answer squared gives us 17.201, or just 17.2 meters squared. Good job.